Hello everyone. So today we're going to start on 6.3 implicit differentiation. So much like a lot of the other things that we have learned in this class, a lot of this topic are basically taking the idea that you have learned from basic calculus and expand it onto what we need to do. So here is no different. So what we're going to be doing is pretty much the same thing. We're going to take a concept that you learned, which is implicit differentiation from last year, and now apply multivariable calculus to it. So let's do a quickly review. So last year, you probably remember that you have learned that an equation between two variables can relate them without explicitly defining a function between them. So an example of that would be the following. An example would be an equation like x squared plus y squared equal to 1. So this equation defines a relationship between x and y, but just not a function. And a relationship in math simply just means that two things are related together, which in this case, x and y are related together by this equation. So this equation defines a relationship between x and y, but it is not a function. Now, however, the idea here is that this equation, even though by itself may not define a function between x and y, it just simply define a relationship between them. But we could have function hidden inside this equation or implied by this equation. Okay? So, however, a function can be defined implicitly. Meaning, they are functions quote-unquote hidden inside this equation. And the word implicit basically means imply. So they mean that this equation, even though it does not directly define a function between x and y, but it could be modified into a function between x and y. Obviously, the problem here is the following. If you look at this equation, I'm hoping everyone understands that this equation is a circle. And a circle by itself is not a function because it doesn't pass the vertical line test. However, we could use part of that circle and make it satisfy the vertical line test. And that's what the implicitly defined function means. It means that I can actually take part of this equation and form a function out of it. The reason why I call implicitly defined because we don't know which one we're referring to. There could be multiple of them. So for example, in this case, this equation can have the following function hidden inside. Now, something important is the following. All the following functions define the following. All the following functions defined y as a function of x. Now, this statement is extremely important. The reason why this statement is extremely important because this statement defines the two of the most important things we need whenever we define a function. And what those two things are? The dependent and the independent variable. So something worth writing down for yourself in this expression right here, when I say define y as a function of x, we're basically defining y to be our dependent variable. Output, our x, is our independent variable. So that relationship is extremely important whenever you're dealing with implicit function, because implicit function by its very definition is that it's not properly defined from the equation. So therefore, you must specifically define which is the dependent, which is independent variable. Don't automatically assume one is independent, one is independent, okay? Because it really depends on how you want to define them. So keep that in mind. So what are the function that's hidden inside this circle? Well, simple. Number one, we have this equation that will represent the top half of the semicircle, which, as you can see, passes the vertical line test. A second function, how about the bottom half of the semicircle? That would also satisfy the vertical line test. And most students would think that, well, aren't these the only two? Well, no. Remember, all I need to do is take part of a circle. That would allow me to form a function out of it. It really doesn't matter how I form a function. So I could be wacky and form a function like this one. And what this function look like? Well, this function looks something like this. Between -1 and 0, you have the top half of the quarter circle. And then between 0 and 1, you have the bottom half. And you have to have an open circle on the bottom so that it would not violate the vertical line test. And that is a function. Well, okay, but this is it's not a continuous function, so we don't like it as much as a continuous function, where it's easy to do math with, but it is a function nevertheless. Okay? Now, notice that in this case, I'm listing these three functions or explicitly. When I write it at this, as 1, 2, and 3 here, they are now referred to as an explicitly defined function. So why is it different? The difference is the following. An explicitly defined function, notice that the dependent variables is isolated by itself. And then we have a formula of only the independent variable on the other side. And that is the characteristic of an explicitly defined function. So when we have x squared plus y squared equal to 1, neither of these conditions are satisfied. That's why it's called implicitly defined function, because it defines relations that might have function hidden inside of it. While in this case, when you list it this way, it's clearly defined that we have the dependent variable on one side, independent variable on the other side, which form a formula. So that's the difference between them. Now, last year, what you learned is the following. For most part, what you have learned last year is technically called explicit differentiation. Almost all the formula that you learn about differentiation are explicitly defined, because you're basically defining the formula of the independent variable only. But in a unit, you learn to do something called implicit differentiation. And the reason why you learn implicit differentiation, because of the following. Oops. The problem is not all equation can be rewritten into explicit form into explicitly defined function. Some can, but some cannot. An example of that would be the following. For example, this equation cannot be rewritten into explicit form, meaning that cannot be written into explicitly defined functions between y and x. In this scenario right here, in this equation right here, notice the symmetry. It doesn't matter which one you try to solve for, you will never be able to isolate y or x by itself. And because of the cubic, the cube power, okay, and also because you have a singleton x and y of the first power, it's extremely hard to actually isolate them, and I don't think that's actually possible to do that. But we are pretty sure that there are functions hidden inside this equation because of the graph. So the graph of this equation looks something like this, if I remember correctly. And yeah, some of you might actually have a little deja vu because it is a function that you might have seen in BC Calculus where Mr. Ambrose or Mrs. Student might show you. This graph actually is something like this. It would go through the origin and then form some kind of loop and then go through the origin again. So that's how the graph of this function look like, I believe. And if you look at this, you can definitely tell that you could have potentially a few explicitly defined function involved. Maybe one of them is this one. So if I take away the loop, I will now have an explicit have a function that will pass the vertical line test. Or I can probably do something else. Let's see if I can think of doing something else. Or maybe we just do the following. We'll take part of the loops. And then before we turn back, we say it's done. That would also form a function. So both of these are valid, implicitly defined function. That is totally valid, totally acceptable. The problem is we just can't find an equation that would do that by looking at the equation x to the third plus y to the third equal to 3xy. And because of that, what we need to do is learn a way to find this derivative without forming the explicit defined function. And that's what implicit differentiation is. Implicit differentiation is a technique that allow us to find the derivative of a function without it being explicitly defined. Okay, so let's quickly review how to do implicit differentiation from last year. So let's just use the equation that we have right now and do it. Okay, so example. The problem will probably ask you for something like this: x to the third plus y to the third equal to 3xy. Find dy over dx. Now, here's something important. Note. The question here, this question, asks for dy over dx. And that's important, which basically means imply we are defining, or actually we will basically define y as a function of x based on this derivative. The reason, because it's defined to be dy over dx, meaning that we're treating the y as our independent variable and a y as our dependent variable and x being our independent variable. In some cases, the question would say specifically saying, assume y as the function of x, find its derivative. And that would mean the exact same thing. Now, before you start this implicit differentiation process, it is extremely important that you identify independent and dependent variable first, because it would change the way you deal with it. Now, of course, you're probably looking at this and say, well, what's the big deal? It's only x and y, right? Yeah, but remember, that's not what we focus on. We're going to try to learn how to do this with multivariable calculus, meaning we're going to be dealing with an equation that have 2, 3, 4, 5, 6, 7, 8, 9, 10 different variables. Some of them are independent, some of them are dependent. And the worst part about it is that because you're also going to be doing partial differentiation instead. So therefore, you have to understand how some variables are treated as constant when you're doing the differentiation and some treated as variable during the partial differentiation. So it's extremely confusing if you don't pay attention to what variables is independent and what will be dependent. Okay, so make sure you get used to and focus on that before you start the process. Otherwise, you get yourself all confused while you're doing it. So in this case, we know that we're treating y as a function of x, and we're doing dy over dx. So this is what I usually do. So it might be slightly different than how Mr. Ambrose and Mrs. Dillon taught you guys. But this is what I do, is I take the equation. I'm just going to basically take the derivative of it based on what the question asked me to do. I'm going to differentiate with respect to x, because that's what the question asked me to do, find dy over dx. So because our first example, kind of reviewing what happened, I'm going to try to write out as many steps as possible so you can follow along the process. So first thing is that would mean that I'm basically taking the derivative of x to the third, taking the derivative with respect to x, y to the third, and taking the derivative with respect to x, 3xy. So let's go through this. So when I take the derivative of x to the third with x, that's simple. That just becomes 3x squared. The problem here is that when I'm trying to take the derivative of y to the third with respect to x, there is a mismatch in our variable. See, here is y to the third, the variable is y. But I'm trying to differentiate with respect to x. And the assumption here is that y is some function of x, and therefore forcing it to become a chain rule problem. Because now I have something inside the third power, and that something is another function that in terms of what x is. So chain rule need to be applied, and chain rule dictate I'm taking the derivative of two things and multiply together. The first derivative I take is what happens when you raise something to the third power. That becomes 3, that's something, second power. And then I need the inside derivative, which in this case is the derivative of y with respect to x, which we call dy over dx. Equal. Here is probably one of the most common mistakes students made. What do you do 3xy? You are differentiating with respect to x, and y is a function of x. Therefore, you now have a product between 3x and y. And therefore, necessitate product rule. So go ahead and do that. So there will be 3x dy over dx plus y times the derivative of 3x, which is 3, so it becomes 3y. Now notice that this equation now have dy over dx in it, which is how it's supposed to work. What you now need to do is to get dy over dx kind of together. But before I do that, I'm going to go and cross out all the 3's. Yes, get into the habit of doing things like this. Simplify the expression as you move along. That way it makes your problem easy to do. And I know last year, Mrs. Ambrose and Mr. Ambrose and Mrs. Dillon probably did not require you to simplify a lot, because that's AP exam does not require that. But that's AP exam. You are past AP exam level. Okay. Now the requirement is different. I would like you to simplify your expression because that makes the math easier to do. Okay. Make all our answer more consistent together. Now what I'm going to do is the following. I am going to go ahead and move the x squared to this side and move the x dy dx to this side. And then factor out. So it becomes y squared minus x dy dx equal to y minus x squared. And then simply divide. Okay, some of you might have it backward, and if you do, it's perfectly okay as long as it's backward on both top and bottom. Something interesting about implicit differentiation that you need to pay attention to is that when you finish your implicit differentiation, you find out that your equation, your formula for your derivative is actually dependent on both the independent and the dependent variable, like in this case both x and y, which is typical. And the reason why that is the case because you really couldn't find out what y is by itself. That's why you kind of stuck with the y variable in your answer, and which is perfectly normal. But also the implication is that it would require you to have both x and y value to evaluate this derivative. Mainly because if you just simply give an x value, you may wind up having multiple y value that you can use, which would now change the derivative. Because you now basically find derivative multiple points that share the same x value. And you think about it, that's kind of weird. Well, it is weird because the fact that you can do that meaning that you don't have a function to begin with, which is kind of the issue right from the beginning. Okay, we have a problem that the graph that we're looking at does not pass the vertical line test. There are multiple points for the same x value. That's why it could have multiple slope for the same x value, which is the reason why when you evaluate, you do need the x and the y in this case. Now, then what are we supposed to do in this year with multivariable calculus? Well, as the name suggests, we're going to try to now find derivative when it involves multiple independent and dependent variable. And so how does that work? Well, the process actually works out very similar. So, but it does require you to think about what you need to do, and also depending on how many independent and how many dependent variable is there. So we're going to probably start with a very simple example for now, and then we're going to eventually move up to a more difficult problem. So let's try this one. So now what happens if you have this? Let's say we're given the equation. Let's say x squared plus y squared plus z squared equal to sine z. Here's the important statement that you need in order to proceed with the problem. Assume that z is a function of x and y. Find dz over dx and dz over dy. So here's probably the most important statement right here. Without this statement, you would not be able to proceed with the problem because you need a definition of which is the independent, which is the dependent variable, which technically speaking is also given based on these two partial derivatives. Because of these two partial derivatives specifically identify z on the top, which is mean that z is our dependent variable, and x and y are both our independent variable. So that's probably the first thing that you want to make a note for yourself so that you know. So in this scenario right here, z is the dependent variable. And x and y are the independent variable. If this relationship is defined differently, it will change the way our derivative work. And therefore, it's extremely important that you pay attention to that as almost always the first thing that you look at. Okay? If the problem did not specify this, then it must specify in the partial derivative that you're looking for. And if the question totally did not give you any of this indication, you really cannot assume which one is independent, which one is dependent, unless it's a word problem. Then you can, based on the wording of the problem, figure it out. But if it's just a simple equation, then you really cannot define which one is independent, which one is independent. Okay, like in this case, we're doing x, y, and z just because we often define z as a function of x and y doesn't mean that that's the only way to define it. Okay, so keep that in mind. The question must specify this for you, otherwise you won't be able to do the problem. So then now how are we going to find dz over dx and dc over dy? Well, let's just go through the step. So let's start with the first thing. I'm going to go and try to find dz over dx. So what I simply have to do is the following, just like what we did before. I'm going to take the equation x squared plus y squared plus z squared equal to sine z. And I basically just go differentiate it. I'm going to partial differentiate with respect to x. Now, why is that partial differentiation? Because in this problem, there are two independent variables. And as we learn, a function that multiple independent variables have only partial derivative. Its derivative is actually called gradient, okay, which is something different. Okay, remember. So here we're basically looking for two different partial derivatives. One for each of its independent variable, x and then y. So does that change the way we differentiate this? A little bit, but not much. So once again, because the first example, I'm going to kind of show you kind of what happened stepwise. So the first thing is that means I'm going to do this. I'm going to be taking the partial derivative with respect to x of x squared, and then of y squared, and then of z squared, and then of let's see if I can squeeze it in, sine z. Okay, kinda. Okay, so now what happens? So let's see what happened when I differentiate x squared with respect to x. Well, that's simple. That's just 2x plus. Here comes the important part. What do I do with y squared? See, if you think about what you did before, you probably say, oh, wouldn't that be 2y dy over dx? And you'll be wrong. Why not? Because in this setup, x and y are both independent variable. And the word independent meaning x and y don't change each other. They're independent of each other. Therefore, you cannot define something called dy over dx because that requires x changes y. Remember, we talked about this in 6.2. dy over dx means how x changes y. And in this case, x and y are independent. They don't change each other. The key here is to understand that x and y are both independent variable. In partial differentiation, we only differentiate one independent variable. All other independent variables are constant. So therefore, in this case, we're basically taking the derivative of a constant that's called y squared. And derivative of a constant is 0. Now then what happened to z squared when I differentiate with respect to x? Now that is different. Why is that different? Because z is a dependent variable. Dependent variable does depend on x, as well as on y also, but in here we only focus on how it changes based on x. So therefore, there is such a thing as dz over dx, which explains how x changes z. Because x does change z. X doesn't change y, but it changes z. So therefore, I have to differentiate like we did before with implicit differentiation. So this becomes 2z dz over dx. And that's equal to sine of z would also have the same exact issue as z squared. So that becomes cosine z dz over dx. So notice the treatment is different between y and z because of y is independent, z is dependent. So now I can try to solve this equation for dz dx. So I'm going to move the dz dx over. As a matter of fact, maybe I'll just move the 2z dz dx over to the other side. So 2x equal to cosine z minus 2z dz dx. And I'm going to go and divide cosine z 2z to the side. So dz over dx is equal to 2z over cosine z minus 2z. So what I'm going to ask you to do is go and try to find dz over dy. Follow the process here. We can, well, we have a few seconds. Let's see if we can quickly do this. Okay, I'm going to do the exact same thing. And this time I'm differentiating with respect to y. So what happened to x squared? Well, x squared is a constant in partial derivative with respect to y. That is 0. Derivative of y squared, 2y. Derivative of z squared. So that behaved the same way as before. That becomes 2z, but dz over dy equal to cosine z dz over dy. So if you do your math quickly, you have 2y equal to cosine z minus 2z dz over dy. So therefore, tell me that dz over dy actually equal to 2y divided by cosine z minus 2z. Notice the symmetry between that and the dz over dx because the equation is kind of symmetrical. Okay? Unfortunately, my time is up for today, so we're going to talk more, do more example tomorrow on implicit differentiation. All right, I'll talk to you guys tomorrow. Bye-bye.